In this video, I'm going to dive in the procedural gear mesh generation process. Purpose of this project is to create solution that generates precision gears real-time in Blender 3D. The reason I decided to make this project is because it takes million hours to model gears manually. And the current gears generator that Blender has, it's 8 of 10 times not usable for precision modeling. So, wanted to make procedural gears like most of the CAD software have. First step of the project is understanding geometry behind the precision gears, or the involute gears, how they are called in mathematical terms. The name comes from the involute curve that characterizes these gears' tooth geometry. These are formulas needed to calculate tooth geometry. Let's begin with the main gear parameters I use as an input. N represents teeth count. Pitch is the distance between two identical points on two adjacent gear teeth. Pressure angle is the attack angle of the tooth. Bigger values, stronger gears; lower values, smoother operation and less backlash. Thickness, tooth tolerance. Mesh generation starts from plane where X resolution is tooth cuts. Then I use this formula which represent tooth width at certain radius. After scaling each cut, I extrude bottom vertices and rotate them along center of the gear. Now there is a spur gear tooth profile. Then I multiply it over circle. And that's it. Spur gear profile is done. But this is far away from the final result, because to make gear usable, it needs to be three-dimensional, and I need to implement parameters like helix angle, chamfer, and the center hole, which is the hardest problem of them because you don't want to use mesh Boolean operations in the Blender geometry nodes, and reason for that is performance. Any mesh intersect, union, or difference operation is extremely slow. This simple example shows how these operations cuts performance. So, to avoid them, I need to think different solution. And the solution for that is to add circle for my generated gear profile, then convert it to curve and fill. And now we came to the part where it gets to third dimension. Variable named thickness cuts sets the amount of cuts along the z-axis. For gears that has 0-degree helix angle, it can be one cut only, if you care about performance in rendering. Things are opposite if there is any amount of helix angle. This parameter is used to smooth gear power transmission. That angle allows to make contact between more than one pair of teeth. After setting helix angle, it needs to adjust thickness cuts to interpolate gear profile rotation along z-axis. The next step is implementing chamfered edge that is used to reduce gear wear. Again, I had to find solution which works without mesh Boolean, and came up with the idea which is shown in this animation. It basically extrudes top and bottom faces twice and shrinks them certain amount. After that, faces that are not needed are dissolved. There is no face dissolve node in geometry nodes, so I found some usable examples in the forums. It required some improvements, but I managed to make them work. Other gear types use the same principle where tooth profile extruded and rotated along different axes. Also, I did basic texture coordinate creation for using procedural textures. I wanted to make these gears 3D printing compatible too. So I tested them on this Wankel engine project. And they work pretty well. Even printed with 0.6mm nozzle, the transmission is smooth. I made separate explanation geometry node for each type of gear that shows step-by-step mesh generation. And I created examples of animated gear sets. These sets are run by animation drivers. Also, there is tool version of these nodes that generates mesh in edit mode. If you want to download these geometry nodes, the project files are in description below.